to me. And what I was interested in mainly is reasoning about the digital circuits. For unrelated reasons, I was working with digital circuits, and I noticed that it was actually non-trivial to reason about digital circuits in a very general way. And I'll get to the details a bit later. And then I was, as I knew a little bit of category theory, and I was exposed to all this work on using commercial categories and related languages of diagrams to reason about systems. I noticed that there was an interesting opportunity to revisit the two-dimensional syntax that's used in in reasoning about digital circuits. Of course, digital circuits are a very widespread technology, and there are all sorts of ways to actually building and reasoning about digital circuits. But I thought there was an opportunity to improve, not just as a notation for describing circuits, but describing the behavior of circuits. Because in terms of reasoning about circuits, most of the tools that are used rely on an idea of simulation, where you put some kind of input, you apply some inputs, and then you observe some outputs. But you don't have the kind of syntactic reasoning tools that you have in programming languages, for example, like operational semantics. So I thought there was an opportunity to try to develop something along the same lines, operational semantics, because obviously in programming languages, operational semantics, so semantics defined by syntactic transformations, is very useful. And I was also intrigued by particular examples that came up in discussions with people who do hardware design and reasoning about hardware, is a category of circuits, or a class of circuits that I thought was quite interesting, which are called cyclic combinational circuits. So these are combinational circuits, but you notice that they have sometimes the output is fed back into the input. And these, where everything here is just combinational circuits, so just gates. They don't involve any memory elements. And if you want to plug in such circuits in conventional tools and you want to reason about them, they will reject them, because these kind of combinational cycles are banned by normal tools that reason about or simulate or reason about digital circuits. However, the behavior of a circuit like this is well defined, and there's no reason to reject them out of hand. It's clearly a limitation into the reasoning tools that we have to apply to such circuits. So that was another opportunity to try to apply these techniques to reason about, to solve actual problems.
You get race conditions?
No, here you don't get any race conditions. Yes?
Do you end up getting memory type behaviors even though you don't have actual memory cell things because of the way it feeds back, or does it actually?
No, these are called cyclic combinational circuits, because although they have cycles, they behave like combinational circuits. Okay. They don't generate memory effects, they don't generate oscillations, they behave as if they were combinations. And I will show you this as an example in the end of actually reasoning about this particular circuit.
Why don't they generate race conditions?
I'll work out this example a bit later, yeah. So, I read this quotation by Freeman Dyson. I think it applies to what you're going to see, just to set the expectations. In terms of the mathematics involved, it's really quite off the shelf. There's nothing spectacular going on. And it's not particularly difficult, but maybe it's kind of aiming at the low-hanging fruit, but I think it's an interesting low-hanging fruit that somebody has to pick it, because the potential for actual interesting developments is definitely there. So again, to set up a bit the framework in which I'm going to operate, primarily I want to proceed in an axiomatic or an algebraic on a syntactic way. So I don't want to worry too much about the underlying concrete mathematical model. In contrast to the talk that you have seen this morning, which started from a concrete mathematical model and then kind of simplified it into a type theory, here we're starting directly at this kind of axiomatic, at the axiomatic level or syntactic level. And all the equational properties that we are going to mention, in some sense, they correspond to physical laws, broadly construed. They correspond to things that we can actually state about digital circuit. This is how they behave. So in some sense, we can say that physical reality is the model that we're trying to capture directly in this way. I'm also going to mention a concrete mathematical model, which is mainly provided to make sure that this axiomatic construction, which can be quite elaborate, it doesn't degenerate in some sense. It's not inconsistent. So yeah, and in terms of the way these equations combine, it is going to be pretty much off-the-shelf category theory. Maybe there is something new there, and maybe the stuff that's new is actually reinvented rather than being genuinely new. So I apologize in advance if I'm not attributing in an impeccably scholarly way whoever invented these things first, but I will try my best. And also feel free to indicate the origins to me, and also feel free to ask questions. Okay, so let's start with combinational digital circuits, and you can quite imagine quite clearly that these form a prop. So you have a signature of components, and these are your logical components, which can be things like gates, like AND gate, OR gates, multiplexer, whatever you want to put in your signature as your basic circuits. But also you can go to pre-logical components if you want to, but stay within the realm of digital and not go generally within the realm of electrical circuits. So you can look at, for example, transistors working in saturation mode. So there's only a discrete number of values they take on as inputs and outputs. And in terms of the values, the important thing is that they form a lattice. So if you want to think about logical circuits, then you're going to have a true and a false. You're going to have a bottom that corresponds to a disconnected circuit, and you're going to have a top that corresponds to an indeterminate or illegal combination of values. In case you want to reason about circuits at the pre-logical level, then you can take a more complex lattice of values, and this is an IEEE standard about digital circuits. And here you have like a low, high, and it's like a low intensity high value and a high intensity high value, and the same thing about the low value, low intensity low and a low intensity high, and they were ordered also in a particular way. So yeah. No. But I just wanted to put it by contrast with logical, because yeah, of course you build this out of this, yeah, and the framework is generic. So in our signature we have these levels that corresponds to our inputs and our outputs, the values that we feed in and that we observe. We have our gates, and we have wires. And the wires have a commutative monoid structure where you can fork a wire. So the forking of the wire has one input and two outputs, and also you can ignore a wire. And this is the multiplication of the monoid, and that's the unit of the monoid. And this is going to be a symmetric monoidal closed category, a free category, because obviously the way we want to think about these circuits is just in terms of how things are interconnected. We don't want to think about the length of wire, we don't want to think about the way the wires are braiding in the actual physical circuit, and so on. And we want also to add some specific axioms. So for example, what we want to say is that all the gates, all the components that we use in our circuits are extensionally characterized. So for every combination of inputs to some component, you have a unique and well-defined output. This unique and well-defined output, of course, can be top, which is the illegal value in some situation. And they're also monotonic over the lattice of values. And the interaction between the value monoid and the wire monoid is sorry, I should have said the value lattice. And the wire monoid is as follows. If you apply a value to a forking wire, you get 2 copies of that value. So it is also extensionally characterized. But it is quite important here for the way how this kind of formalism works, that all these gates have arbitrary input arity, but they produce one single output.
The unit corresponds to true. You said forking corresponds to
Forking is this.
It's also like a termination one,
There is a.
Does that have anything to do
So I call this is F and this is W.
Does that have anything to do with true?
No,
That one doesn't.
no. Everything you put here,
Should that be F tensor F?
no. So this is F composed with V is same as V tensor V.
This one down the bottom is not.
This one down the bottom, no. Now we have some immediate consequences that we can compute from this setting. First of all is that all circuits are extensionally characterized. So when any morphism I create in this category, if I give it a set of inputs, I get well-determined output, and they're also monotonic. And also, more importantly, this category is Cartesian. So if I take, so first of all, the 0, which is this is the 0 type, is a terminal object, so we can show that. And every circuit where I share the outputs, I can equally create 2 copies of the circuit and share the inputs instead. So the forking wire behaves like the diagonal in the Cartesian category.
Sorry, I missed what these are immediate consequences
Of our setting, of this and this.
That's not a mathematical derivation.
Oh, here you say all gates are existentially characterized.
Yeah, and here is
immediate
all circuits.
consequences. Oh, all circuits.
Yeah.
Ah, okay.
Yeah.
See.
So as much as possible, when we try to introduce an axiom, we would like to have small axioms, which are axioms about components rather than big axioms about the circuits in general. So the properties of the circuit, it's more satisfactory if you can derive them rather than postulate them. And most of the time we can derive them, and when there are exceptions, I will point them out. Also, we can derive stuff about the behavior of wires, the fact that the forking wire, the joining wire, the unit of this W and the disconnect, together they form a bi-algebra. So this wire structure is the same as this wire structure. And finally, joining 2 wires and forking 2 wires are inverses in this sense. Here's another less obvious property that, so if we do this, splitting a wire and then joining a wire, that's the same as the identity all the time. But sometimes, so here we have a joining of the wire followed by the splitting of the wire. So in a loose sense, very loose, I can say that in this particular circuit context, I can replace this green wire by these 2 green wires. So it's almost as if in a particular context, F composed with J, it's also a bit like an identity. Okay, so this is kind of a derived property that is going to come in handy later. Yeah, because these are these can be reduced to just values eventually in any context. Right, now let's extend our language of circuits by adding delays. There are several ways in which you can deal with delay, but probably a simple and interesting enough way is just to look at it as a special morphism of type with 1 input and 1 output. which you can think of it as the smallest observable delay in your circuit. And therefore you can think of these as time circuits. If you make a sequential composition of these delays, you can represent longer or shorter delays. So these are timed circuits rather than synchronous or asynchronous circuits. I will come back to this distinction because this is quite an important distinction. But I will only talk about it in the conclusion. And there are two axioms that we associate with the delay. The first one is the axiom we call timelessness. So if you put a delay at the beginning of a gate or in front of the gate or behind the gate, you get the same thing. And in reasoning about digital circuits, there is like in actual practical digital circuit design, there's a name for this called retiming, that if you have memory elements, you can commute them with the logical gates, which are instantaneous. And that you can do that in a way to optimize the behavior of your circuit. And there's another axiom that is best if you look at it visually. So if I have any gate, so any element of my signature, and at the input I have some values that arrive immediately, and here this wire contains delays, I can split my gate into two components, into two copies. One of it deals with the immediate values, and one of it will deal with the values that arrive later. So this is like a very restricted form of coproduct. You can think about it like that if you want. That only works in certain contexts. In this particular context, I can push a gate along a joining of two wires. So with this delay, I can, in place and the joining of the wires, I can define a notion of streams, where a stream is simply a value and then join with a delay and then another value, and then a delay and then another value, and then a delay and then another value, and so on. So that's how a stream of inputs would look like. And the behavior of any circuit is also well defined on these streams. So I can, for every circuit F and any input stream S, there is a unique and well defined stream, which is the output stream. And the category is still Cartesian, and this can be proved. Now, to make things really interesting, we add the notion of feedback. And now we have what's called sequential circuits. So they're digital circuits that have logical gates and also feedback. But unlike the notion of sequential circuits that's used in digital design practice, we make this feedback unrestricted. We don't require the feedback to go through a memory element. It can be instantaneous feedback over logical elements. So how do we do that? We freely add a trace operator. And again, this is kind of the freedom that we get because of the syntactic approach. We know that with a digital circuit, you can do that. You can take an output and then feed it back into the input exactly in this way. And you know, maybe what's going to happen is not good, but you can always do it.
So, in the example with the delay, your circuits, your K always compute like in 0 time.
Yeah.
It's instantaneous.
Yeah.
Okay.
Yeah, and you can see how if you want to model a circuit that computes with a delay, you just create a combined circuit between an instantaneous computation, an instantaneous gate, and a given delay.
Yeah.
And then you have circuits with delay. Yeah. So here is in the algebraic structure. Here we make a requirement which is kind of a big requirement. So it's a big axiom. We require that 0 is a terminal object. Before we had feedback, we could prove that 0 was a terminal object, but here we can't. And this is kind of the equality that we cannot really prove So if you have a gate, and if you just take a feedback on one of the inputs, so you're left just with one input and no output, that it's just like a wire that's ignored. And that is very nicely related to the discussion, I think, that we had before lunch, which was talking about ways of describing causality. And digital circuits are very causal. It's a very well-defined notion of input, and it's a very well-defined notion of output. And you have a very well-defined flow of information. And all these results that we had so far about extensional characterization tell you that the input is defined by the output in a particular way. But this is something that we have to stipulate. And this is a commitment to the fact that, I don't know if it has to do with causality or if it has to do with the fact that we are committed to this extensional view of circuits. So the only property that we observe is the output. Of course, if you wanted to observe other things about your circuits, like how hot they get, or how much they weigh, or how much area they consume, of course, that would be no longer an equality. Another handy property that is very easily proved at the level of diagrams is that for any circuit, we can find a trace-free circuit that we can obtain our given circuit just by applying the trace global. So we can take all the little feedback loops and pull them all in global scope. And that's a property that simplifies reasoning about feedback gradient. And as I said, for this language of circuits with feedback and delay, because it is quite sophisticated, and you don't want to rely completely just on your basic intuition. It's good to have a concrete model to show that your axioms are in fact sound. And it is the model is a model of infinite streams and functions over infinite streams. But there is an interesting question here, because the axiomatization that we use is not complete for these models. So it's just a sound axiomatization. But this model itself is a model that seems to correspond quite intuitively to the way you expect circuits to behave. But if you want to reason in the concrete category, you can do more calculations and you have more reasoning principles. Okay, so consequences of these kind of extension of our circuits by adding feedback is, and that's something that is maybe somewhat surprising, is that this category is still Cartesian. So in some sense, if you take this extensional view of circuits looking just at the input-output behavior and you add feedback, we still have Cartesian. And most of the cases of the proofs are straightforward. The only one that is interesting is this one. What happens if I have a circuit with a feedback loop and now I want to share the output? Well, I can introduce using this equation, I can introduce a split and a join in the wire. Then I can rearrange my circuit like this, and now I can see that inside this blue box I can apply the induction hypothesis. And then I can rearrange my wires like this, and then I can apply the lemma that I had earlier. And now I can move this loop inside, and this is what I wanted to prove in the first place. Now the consequence of this, and this is really what something that was the objective that we had in mind all the time, is the fact that we knew, it's something that is been known for a while, that if you have a trace monoidal category where the monoidal tensor is product, then you can define an iterator. And the iterator is something that has diagrammatically this property. So an iterator is, you can see that the output is feeding back, and what I can do now, I can unfold my iterator. I can create a copy of my circuit. And this is really the key property that you need in order to reason syntactically about anything. That's what happens when you want to reason syntactically. When you want to write an operational semantics of a programming language, the thing that's really, really important is the fact that you can unfold your recursion operators by creating a copy. And that's exactly what we can do now in the context of digital circuits. Now, what are the basic properties in this setup? Another one of them is diagrammatic, and that's going to be helpful, is that we can write our circuits in a particular way as a composition of things where every stage in this composition is something that has only identities except for one component, which is not an identity. And then, with that, we can show that. Oh, did I mention what passive is? Maybe not. Another. Okay, so here I mentioned passive. Yes. So a passive circuit is a circuit. Yes. In constructing our circuits, we don't make a distinction between gates and inputs. Inputs are taken, these value levels are taken just as a component. But these inputs are active components. You can take all these inputs out and put them in a global. So if you have a circuit like this, you can write it like this, where you just everything that is an input is just pulled outside, and what's left in here is passive. So it has only the gates. And if you have such a passive circuit, so a circuit that doesn't have these hidden values inside of it, which is, of course, if you want to build a circuit that has these values inside of it, that's not a physically viable circuit anyway. It's a weird kind of a thing to build. So a circuit without those hidden values, which is passive, it's also subject to the streaming property, in the sense that if you feed some immediate signals and some delayed signals, you can copy your circuit. And a copy deals with the immediate values, another copy deals with the subsequent values. And now, because of kind of standard connections between trace monoidal categories and graph rewriting, all the equations that we had so far can be expressed as graph rewriting rules, which are quite simple, and they're specific graph rewriting rules if we represent our circuit as a graph. So this is the simplification of a gate. Given the values, it's replaced with its value. This is a value hitting a split wires, and then we copy the value. This is the streaming, where we copy a gate to deal with the immediate and the subsequent values. This is using the fact that W is a terminal, that 0 is a terminal object. And yeah, so these are the little rules, and we also have a big rule that corresponds to the unfolding of the circuit, and this is the really important rule that makes things work in an interesting way. So first of all, I'm putting my my circuit in global delay form. So I take all the delays and I move them outside. I put them here in front of the circuit. That's obviously possible. I just you can think of all these delays as being just yanked out, and all the wires extending in the appropriate way. And also I'm putting all the feedback, all the traces in global form. So these are the traces that go through delays, and these are the traces that don't go through delays. And I know that I can iterate, right? So this is given, as you can see, this is given as a this is given as a trace, not as an iterator, but you can calculate a trace out of an iterator and an iterator out of a trace. These two are determine each other. So this is how the unfolding of the iterator given as a trace would look like. And the next step, we're pacifying this circuit by extracting all these values that might be scattered throughout and putting them as an input to the circuit. And now, because this is a passive circuit, we can use the streaming axiom. And this is it. So now, here you can see we have a copy of the circuit here pacified, a copy of the circuit here pacified. We have a bunch of inputs. These are the bottoms. These are disconnected wires at the input. This is a disconnected wire at the output. But here, both these instances of the circuit, they don't have any they don't have any feedback loops involved. So we can push these values, these input values through, and we can kind of also push these ignored outputs in, so that these two circuits can be then simplified. And in the simplification, you can have two situations. You can have a simplification which is productive, or you can have a simplification which is not productive. Productive would mean that after I bring the circuit to this form, depending what's inside these two circuits, I can rewrite everything in such a way that I can basically get rid of this delay here and then have another unfolding and another unfolding and so on. And as it is well known that a delay guarded circuit, so a delay guarded circuit means that all the feedback loops go through delays. So we can prove that, as expected, delayed guarded circuits with no open inputs, so all the inputs are actually hold actual values, are going to be productive. So we can always unfold, and on every unfolding we can get some new information out of the circuit. So we can simulate this circuit. But something that was not done before is that we can have an effective characterization of unproductive circuits. So we can prove that after one unfolding of the iterator, if there's not enough information here to simplify this circuit so that you get some output out of it, then you are stuck there forever anyway. So you don't have to carry on hoping that you're going to get some output eventually. You know that if one unfolding is unproductive, then you can stop. You're never going to get anything out of this circuit anyway. And this is a new result, and this obviously helps when you want to simulate an actual circuit. Right. The initial example was reasoning about cyclic combinational circuits. So now, how can we reason in this system about cyclical circuits that have about combinational circuits that have instant feedback? So here is a very simple circuit. This is an OR gate. This is an AND gate. We are putting the true value going in here, and we're feeding back this value here, both into the OR gate and into the AND gate. And if you take this circuit and you describe it in a standard hardware description language and you feed it in existing tools, it's going to be rejected, because you get this check that says every such feedback has to go through some memory element. And this is here not the case. But we can reason about this quite easily in this syntactically. So we just propagate the true value to both circuits. Now here, both the circuits are extensionally characterized. So that means that this circuit can be simplified to that. And now this can be deleted because it goes to the zero object, and it's the wire monoid. Now this guy has both its values like this, and I'm left with this kind of weird circuit that has a loop it's not really quite just a value. You still have this trivial loop here going on, but that can also be gotten rid of just by applying our unfolding rule. So we can unfold this rule like this, and now this goes to 0. So and also this goes to 0, and both can be removed. So now I just have the value of true going straight out. Also, something that's new is that these methods can be applied to abstract circuits. So circuits where some of the components are not known, are black box. And again, these are, if you have these kind of black box circuits, then obviously you cannot use simulation on them. So this is the circuit from the very beginning, where you have F and G, we don't know what they are, they're just black boxes. And these M are multiplexer. What's a multiplexer? Is a circuit that it looks at this input, the third one. If it's true, it allows the top one to go through. If it's false, it allows the middle one to go through. So now what I'm going to do here, I'm going to do a partial evaluation, which is again something that simulation-based methods cannot handle. So I'm supplying one input. Here, I'm not supplying any input, and now I'm going to see how is this circuit going to be simplified without knowing what F and G are. So as I said, I skipped over some steps. So this true is going to be propagated by these green wires to all three multiplexers. And now I can replace the multiplexer by its behavior when the control signal is true. So now you can see that these guys become either blocked or they're allowed to go through. Now I can simplify by removing all the garbage wires, and I'm left with that. And you can see that now this is a combinational circuit because the information goes into G, loops around here pointlessly, and now goes into F. And here, if I was to put false here, then I would get, instead of F followed by G, I would get G followed by F. So in fact, this whole circuit, you can then prove that it's equivalent to, if control circuit, then F of G of X, else G of F of X. But it's a clever interpretation, a clever implementation, because if you just follow kind of a syntactic translation of this into a circuit, you would need 2 copies of F and 2 copies of G. Whereas here, you can get by just with 1 copy of F and 1 copy of G. And finally, you can apply the same techniques to pre-logical circuits. So this is exactly the circuit that I had before, this one, except that the multiplexers have been implemented down to transistors. So now this is a bit too small to read, but you can see that some of the, where it says B is the black box, and every little thing here, see the P and the N are the PMOS and the NMOS transistors. So I have a circuit here that I know the control signal, and I can simplify it down to this circuit. And this is also something that is new, that simulation-based tools cannot do. This is completely syntactic application of partial evaluation, and this is the residual circuit. So I think that this is a fairly convincing coming together. On the one hand, you have category theory that gives you the principles of equational reasoning that are absolutely essential to be able to prove that all these rewrites are sound. On the other hand, the string diagram representation, the graph rewriting representation, is very important in order to do effective and efficient computation. Because the simplification of the circuit from here to here, you could not do it just on the term model. Because the term model has the functor, the monoidal tensor doesn't have a clear direction. So it would be very difficult to explore all the distributions to reduce the circuit. Whereas once you construct the string diagram representation, you can compute on it globally and efficiently. And I was also I presented this this at the conference called Formal Methods in Computer-Aided Design, and I spoke to engineers, and I was very happy that they didn't think this was completely mad, and they thought there was potential usefulness here, because it really can do things that, in terms of circuit analysis and reasoning about circuits, this method can do things that simulation-based methods cannot even try. And also, I want to say that the theory, most of it is completely off the shelf. Some of it, I rediscovered it. Some of it, I found it maybe not in the original papers that proposed it, but particularly influential to me were works by these people, and these are the main references of this of the work that I have presented. So, in conclusion, we are working on implementation work because it is actually possible to build tools to reason about digital circuits based on these methods, but it can be, to do it properly, it can be quite laborious. But there are two abstraction gaps here that this, I think, this work exposes and bridges a little to some extent. The first one is the distinction between electrical and digital circuits. A digital circuit is obviously a kind of electrical circuit, but it's an electrical circuit seen at a certain level of abstraction, and by raising the level of abstraction, we get more axioms and more reasoning principles. In particular, at the electrical circuit, the way you would model an electrical circuit is in a compact closed category, whereas the digital circuit, it's in a trace monoidal category with a Cartesian product in these categories with iterators. And the fact that you have the iterator, it allows you to reason syntactically. Whereas in the electrical circuit, in the compact closed setting, you cannot do that. You cannot unfold a feedback loop. And also the behaviors of the wires are different. In the electrical circuit they have Frobenius laws, whereas in the digital circuit, they have bialgebra rules. But it's quite obvious that I said that one lives somehow on top of each other, or it's an abstraction of the other. And that would be nice to see some work trying to bridge this gap. The second gap, which this kind of exposes, is the one between timed versus synchronous or asynchronous circuit. So here the time is measured, and that is when you want to do actual practical simulation, keeping track of the time is computationally intensive. What you might want to do is to reason at a higher level of abstraction about time. Asynchronous circuit says that there are delays, but I don't know what the delays are. Synchronous circuit says there are delays, but they're not fine-grained, but they're just kind of these big chunks of delays. And everything happens in these big chunks of delays. Both of these are abstractions on top of the time circuit, which are non-composition. It's very easy to come up with examples to see that the time circuit, there's no like obvious functor that would take you from the time circuit to the asynchronous abstraction or to the synchronous abstraction. And in the case of the asynchronous abstraction, if you want to go to asynchronous, then you lose, for example, having a Cartesian product, because you no longer have this ability to create exact copies of the same circuit because the delays are non-deterministic. Even the identity becomes a problem. And synchrony, it's also a problem with respect to composition, because when you have two time circuits, if you want to make them synchronous, so that means certain distinctions between timing are going to be obliterated, then in composition you can either introduce deadlocks or resolve deadlocks. It can go both ways. So it is all it is again something that would be worth that would be worth studying and understanding a little bit better. And what I believe is that this framework, by looking at kind of these string diagrams presentation, is something that can help in both cases in the future. Thank you. Synchronous circuits are, so you have, it's like this, you have a bunch of events that happen like this, and this is the timed model. And synchronous, I'm taking a granularity of the time which is kind of larger, and everything that happens within one clock cycle I just consider to be simultaneous.
In the top one, isn't that this 7 clock cycle? How do you think?
Oh yeah, you can reduce your clock cycle, but yeah, so that's why I say you can say what is the smallest observable delay. But if you make your observable delay very, very small, then you kind of you lose the you end up with the time circuit. So, but what you want to do in a digital in a clock circuit, you really want to just to simplify reasoning. I just don't want to think of all the ways in which everything that happens in a particular cycle is interleaved. I just want to say,
like moving from binary to ASCII allows you to.
Yeah, something like that. Like it's like
From a single clock to
it's like I'm
multiple clocks.
closing my eyes. I'm closing my eyes, and I'm only opening my eyes at the particular times, and everything that happens in between, I don't care.
It's also a difference between one computer and a network of those things.
Sorry?
The difference between having a single computer with a single internal clock and having them communicate over a network.
Well, of course, because these are abstractions of time systems. You have even deeper problem when these things have to compose with each other. Mm-hmm. Because synchronous circuits can compose in an asynchronous setting. So you have things like GAL circuits, like elastic circuits, and you can also have asynchronous circuits that have synchronizers that they get. Yeah. So it's a lot of ways in which time can be abstracted, and the problem is that none of these abstractions is compositional, and they're not really. They're more like the way they're dealt with in practice is more like by design guidelines rather than by semantic models. So the fact that you don't want to have combinational feedback, instant feedback, that's a design guideline. It's not a necessary restriction. It's something that you rule out some circuits out of hand so that they don't raise problems. And there are all sorts of design guidelines like this too, so that you can fit within a particular framework. Yeah.
There was beside Casanescu and Stefanescu, there was one the student of Georgi who actually tried something related with adding a specific delay operators like that one. But the same school actually at the certain point started thinking about how can I say, wherever feedback is not instantaneous, which how can I say, add actually some delay in it. And the key idea is that if you have the symmetry and you apply the feedback, you don't have the Yankee anymore, but you have some kind of delay. Have you tried to look at that? Because at the time it was nice because it was also related to the int construction of the graphs.
Yeah, but like if you start tweaking, and in the end what you don't want to do is to lose the fact that you have a trace monoidal category where the monoidal tensor is a product. Because if you lose that, then you cannot unfold your feedback, and then you have a lot less syntactic reasoning that you can do. It's very important to be able to unfold and keep reasoning by unfolding the circuit. And that's the problem with all these kind of, I would call them non-compositional, because if you say you cannot yank the trace, I would call this non-composition. It has like an arbitrary restriction. And they all lead you to losing this, this kind of very important property. Where's the question? Yes? Well, yeah, Allium did an implementation, yeah. And yeah, obviously that's how we computed this. This was not done by hand. So the thing is that every rewrite rule is linear in the size of the circuit. So it's efficient enough. I mean, and at least at that level, at the asymptotic level, every step is linear, because the rules are very simple. So it's very easy to kind of keep track of the redexes. These are not arbitrary rewrite rules where you would have a hard time figuring out what subgraph you're going to be replacing. These are very simple, and they always they're either from the input, so if you know what your inputs are, you can push them in, from the output, so if it goes to 0, you can push it in, and then there's one big rule for the unfolding. Yeah, and that's also, because what you do, you just copy the whole circuit, and that's also linear in the size of the circuit. It's nothing, there's no combinatorial explosion there.
But in this case, you're taking your boxes that are like logical circuits, and then you expand them to the pre-logical circuits.
In this case, yes.
Yeah, and then you just glue the.
Yeah.
And then there's some form of, I don't know, super compilation.
Yes. Yeah. Exactly. Yeah.
I have a sort of strange question. So you had these, and you check your conclusion slide there?
Yeah. So this compact closed Frobenius world. Well, at least the compact closed part reminds me a lot of quantum mechanics. Frobenius is like the specific basis for this. So that's your physical level. And then you have this trace monoidal closed bi-algebra world. That reminds me a lot of the category REL.
No, this is more like sets and functions, I think.
Are okay. Sets of trace monoidal.
No. It's. I mean, we have a concrete model
So everything
here.
relevant trace.
Everything is a binary. Rel plus is
That's
a trace minimum.
Right. So rel with plus is trace monoidal, and every object is a Fine. So
Yeah. So this is our model, our concrete model. It's streams of values and monotone functions over strings of values.
yeah. So my strange question was that seems to be well, there's something like the world of physics and then the world of logic.
Yeah.
And it'd be nice to really make that sharp.
Yeah,
It'd be nice
yeah.
to like come up with some relation, two different kinds of categories or two different
Yeah.
categories, and then so not everything physical fits into the world of logic. because
Exactly.
The physical world can do stuff that is
Yeah.
well modeled by a certain by
Yeah. Exactly.
So there's not a functor going that way. So is it a functor going the other way? Or what's the relationship between these two?
I think there is some kind of a sound, like
Computer.
when you do calculations here versus when you do calculations there. Sometimes here you will get some values, whereas when you do the same calculations here, you just get top, which is undefined. So it could be anything. I just couldn't figure out. So there has to be some kind of soundness result. You wouldn't get, you shouldn't get 7 here and 3 here. You could get 7 here and nothing here. But whenever you get something here, you should get the same thing here. So it's
Does that mean that any circuit in the second one you can interpret it as a circuit in the
yeah. So and that's actually I think a good test bed for this theory would be looking at pre-logical circuit, because transistors is something that you can look at them input-output, but you can also look at transistors relationally, where you look at it as a constraint system between the 3 ports. And then, so here, the way this is evaluated here is just by rewriting. But also you can say, well, let's just build a big constraint system and solve it, and then you get your kind of your results. And when you do it like this, you would always get some results that when you do it by kind of constraint satisfaction, you get some results that here you would just get things that are not valid. Yeah, I think that would be something that would be very nice, because there is still an abstraction gap. I mean, why is it that and also of course you can have hybrid circuits that combine digital aspects with non-digital aspects, and these cannot be modeled at all here. But if you had the relation between them.
Yeah, I'd be nice to drive. You have to just take some simple example of a feasible category and a logical category and figure out what kind of map it is.
Yeah.
I think we have any more time for questions, but thanking Dan.
Thank you.
We're now all going to, as quickly as possible, go downstairs where there is a bus waiting for us. It will take us to our coach and a dinner.
You should ask if the source code